At 4:12 on 5 October 2025, a precision campaign entered execution. 14 unmanned aerial vehicles launched from concealed rails deep inside Ukrainian-controlled territory. Each airframe carried a 40-kilogram warhead engineered either for fragmentation or semi-armor penetration. The operational directive was succinct: neutralize Port Olia 4 and render her cargo irrecoverable. That objective required surgical accuracy, layered intelligence, and a concept of operations that exploited predictability and concealment rather than brute force. Port Olia 4 was a high-value maritime node, a Russian-flagged cargo ship of approximately 4,900 gross tons, anchored in the Caspian Sea, roughly 800 kilometers from Ukraine's nearest front. Intelligence analysts assessed her manifest to contain nearly 5,000 tons of Iranian-supplied military components, avionics, GNSS navigation modules, precision gyroscopes, electrical systems, and pallets of 122mm rockets. Operationally, that manifest equated to hundreds of loitering munitions and weeks of strike production if delivered to assembly lines. Denying that stockpile promised immediate operational friction and strategic leverage. Planning fused multi-domain reconnaissance with tradecraft. Commercial synthetic aperture radar, or SAR, provided persistent detection irrespective of weather or darkness. Analysts cross-referenced SAR returns with hull geometry, anchor chain signatures, and drift patterns to confirm identity. The ship's decision to anchor inside the Volga-Don Channel rather than in a busier, more obvious berth reduced some exposure but created predictability, a reproducible 4 to 6 hour anchor window. Signals intelligence complemented imagery. Intermittent radar emissions produced a heartbeat signature despite enforced radio silence. That combination of space-based SAR, maritime pattern analysis, and SIGINT produced a time-sensitive targeting opportunity. Commanders selected an effects-based objective, not indiscriminate destruction, but a controlled sinking. The attack had to open the hull in locations that would flood critical compartments, disable damage control and firefighting systems, and send the ship's cargo to the seabed, where salvage would be impractical. Achieving that required precision in munition selection, trajectory planning, and sequencing. The strike package used indigenous UJ-26 extended-range kamikaze platforms, composite airframes with reduced radar cross-section, GNSS and inertial guidance hardened to jamming, and electro-optical terminal seekers for final confirmation. Performance parameters were deliberate: sea-skimming approach altitudes in the 20 to 60 meter band, cruising speeds of 150 to 180 kilometers per hour, and an operational radius approaching 1,200 kilometers with 2 relay drones reserved for high-altitude telemetry and command relay. 14 drones were allocated, 12 attackers and 2 relays, divided into 4 axes of attack to produce cascading system failure. Axis 1 to strike propulsion and stern systems, Axis 2 to target the bridge and bow control spaces, Axis 3 to rupture midship structural integrity, and Axis 4 to lay denial effects at approach lanes to obstruct tug and patrol access. The approach profile sought to exploit littoral clutter and automated coastal filters. Low observable returns registered as small, fast maritime clutter and were deprioritized by coastal radar systems. Commanders calculated a compressed time-on-target window to deny defenders the opportunity to sequence an effective response. In the hours before launch, telemetry loops fed back environmental and navigation updates. Flight commanders monitored fuel reserves, GNSS quality, and electro-optical locks. 2 high-altitude relays provided persistent overwatch and allowed dynamic adjustment of final approach vectors in response to emergent defenses. The strike plan emphasized synchronized impacts to create concurrent failures, electrical loss, pump disablement, and progressive flooding rather than a sequence that defenders could stabilize. In short, the operation traded mass for precision, and predictability in the target's anchorage paid the operational dividend, an achievable strike without the need for a conventional naval engagement. At 9:15 local time, terminal engagement was initiated after final confirmation of visual and sensor lock. The first phase of the attack aimed to remove the ship's ability to fight its own fires and sustain dewatering operations. The intent was clear: breach critical systems and force conditions under which salvage and recovery would be impractical. The hunt had become a decisive strike. The Caspian, regarded as a rear sanctuary, was about to be contested. Execution adhered to the plan's choreography. Attackers remained in ultra-low cruise envelopes to avoid horizon-based coastal detection, while 2 relay platforms ascended to high altitude to maintain line-of-sight telemetry. The swarm's flight parameters were tuned for littoral penetration: sea skimming altitudes between 20 and 60 meters, speeds balancing terminal stability and range, and guidance architectures blending GNSS, inertial navigation, and electro-optical terminal homing to mitigate jamming or spoofing. At 9:15, the terminal sequence began. The first UJ-26 impacted the aft upper deck adjacent to the engine room ventilation trunk. Its semi-armor penetration warhead ruptured ducting and ignited fuel and lubricants, producing a fire that propagated into cable trays and control conduits. That initial effect was engineered to cascade. Damaged control circuits tied to the engine room were compromised. Emergency pump actuation was degraded, and automatic suppression systems began to fail under heat and electrical disruption. Within seconds, a second impact struck the starboard waterline, breaching hull plating below the main deck and enabling rapid ingress to lower compartments. The third and fourth strikes targeted midship and a cargo hedge, respectively. These effects were sequenced spatially to induce asymmetric flooding, thereby shifting the ship's center of gravity and increasing torsional stresses on longitudinal members. By 9:18, a deliberate hit on bow control spaces produced catastrophic electrical distribution failure. Distribution panels shorted, main bus trips occurred, and emergency power loading exceeded the automatic transfer capability of backup systems. Automatic firefighting and dewatering systems dependent on electrical actuation were rendered unreliable or inoperative. Between 9:20 and 9:23, a tandem impact shredded a large section of starboard hull below the waterline, overpressurizing adjacent bulkheads and overwhelming design margins for localized damage. Warheads with delayed fuse penetrators created deep cavities where portable pumps could not effectively reach, ensuring slow, progressive flooding that compounded with fire to make human damage control increasingly untenable. Denial drones simultaneously executed near-surface detonations in approach lanes to create underwater shock and floating debris, obstructing immediate tug and patrol access and prolonging the critical window for mission accomplishment. Defensive response was constrained by the compressed engagement timeline. Coastal radars and air defenses acquired low-altitude returns and engaged, but 2 attackers were intercepted during terminal runs. But interdiction occurred too late to prevent the sequential breaches from achieving their cumulative effect. Rescue tugs and patrol craft steamed toward the target, but encountered burning fuel films, debris, and active denial effects. Thermal conditions coupled with structural distortion limited the efficacy of onboard firefighting teams and made patching and dewatering operations hazardous and ultimately insufficient. At approximately 09:25, the commanding officer ordered abandonment. Lifeboats hit the sea as the list increased, and fires continued to spread amid ruptured fuel lines and exposed wiring. By 09:28, additional strikes severed propulsion shaft lines and released fuel into voids under hot deck plating. Fuel that ignited contributed to floating oil films and intensified deck-level conflagration. Under combined hydrodynamic and thermal stress, structural members yielded and progressive hull fractures accelerated the path to capsize. Throughout terminal engagement, relays transmitted high-definition imagery, enabling command elements to assess hit sequencing, fire progression, and damage states in near real time. Data confirmed the strikes designed to create multi-vector failures, fragmentation to disable exposed systems and personnel, and penetrators to ensure deep, hard-to-reach breaches that prevent effective dewatering and repair. Damage dynamics followed a classical failure cascade: localized system loss, propagation through integrated systems, asymmetric flooding shifting the center of gravity, and structural fatigue culminating in hull failure. By 09:37, Port Olia 4 reached an irrecoverable damage state. Motion sensors and visual telemetry indicated imminent capsize and sinking. Over subsequent hours, the hull failed and the vessel settled on the Caspian seabed. Satellite imagery captured the residual smoke plume and oil sheen as daylight progressed. Salvage attempts commenced in the days that followed, but the combination of depth, fragmentation and contamination meant that a large portion of the manifest was unrecoverable or recovered only in degraded condition, materially denying the attacker the major share of components and ordnance. Operational analysis of the strike highlights critical enabling factors: integrated multi-source intelligence for target identification and windowing, low observable sea-skimming long-range unmanned platforms hardened to EW, and a precisely sequenced effects methodology that converts multiple small impacts into a single strategic outcome. The engagement validated an emerging operational concept: long-range unmanned systems, when coupled with superior targeting intelligence, can project lethal effect across maritime rear areas once considered beyond reach. The Caspian had become, in a single operation, a contested domain. The sinking of Port Oleafor produced cascaded strategic effects that extended well beyond the immediate material denial. At 13:19 local time on 5 October 2025, satellite confirmation of submergence established the operation's physical outcome. The tactical success translated rapidly into operational friction, commercial disruption, diplomatic alarm, and a psychological shock that altered behavior across the Caspian littoral and the wider logistics network. Material denial was immediate and tangible. Intelligence had cataloged nearly 5,000 tons of critical components: avionics, GNSS packages, guidance gyros, electrical systems, and explosive ordnance, sufficient to support hundreds of loitering munitions production cycles. Salvage operations that began days later recovered some material. Much was found corroded, fragmented, or otherwise non-serviceable. Reconstitution of those production lines required time, procurement, and alternate sourcing, precious weeks and months in a campaign environment. The attacker had bought that time deliberately. Attrition of material inputs imposes tempo costs on strike generation that can produce operational pauses and protect friendly systems. Commercial and logistical networks reacted within 72 hours. Shipping registries and underwriters repriced risk for Caspian routes. War risk premia increased sharply, and several insurers withdrew blanket coverage pending renegotiation. Shipmasters adopted AIS darkening and other operational security measures to reduce trackability. Port authorities instituted additional inspection and escort requirements that lengthened turn times and inflated logistic costs. Some shippers rerouted cargo overland, accepting higher transport costs to avoid contested maritime corridors. The immediate effect: increased friction and costs for sustainment that ripple through supply chains dependent on Caspian transits. Behavioral changes were both systemic and granular. Crews demanded hazard pay and contractual indemnities. Private operators sought state guarantees to remain economically viable on contested routes. State logistic enterprises with deeper balance sheets and political backing consolidated position as carriers with capacity to underwrite increased risk. Militaries revised littoral defense postures. Investment in coastal radar density, sensor fusion for low-altitude detection, and layered counter-UAV solutions became urgent priorities. Anchor doctrine changed. Predictable anchorage windows were now liabilities to be minimized, and dispersion, camouflage, and hardening became operational directives. Diplomatically, the incident compelled emergency consultations among Caspian littoral states and international stakeholders. Concerns ranged from escalation risk and rules of engagement to transboundary environmental impact resulting from burning fuel films and munitions residue. Neutral states with economic exposure in the Caspian sought to insulate commercial traffic while avoiding entrapment and broader geopolitical confrontations. Political messaging from struck parties attempted to minimize the event. Open-source investigators and commercial imagery analysts rapidly authenticated evidence, eroding denial windows and magnifying the strategic signaling achieved by the strike. The psychological effect may be the most enduring. Where distance had formerly conferred sanctuary, it now conferred vulnerability. Commanders who had planned logistics around rear area aggregation recalibrated to embrace dispersion, redundancy, and concealment. Decision cycles elongated as risk acceptance thresholds rose and political considerations about material exposure became more salient. Commercial captains, supply chain managers, and insurance underwriters all operated under heightened uncertainty. Each small radar blip carried the possibility of lethal consequence. Environmental and humanitarian implications complicated the aftermath. local fisheries and coastal economies experienced short-term disruptions from contamination and restricted access. Burning oil films and scattered munitions demanded mitigation efforts that introduced additional costs and coordination requirements. While such environmental impacts exist in the shadow of military operations, they also became part of the diplomatic ledger in subsequent negotiations and safety briefings among littoral states. Strategically, the operation validated a doctrine of effects-based interdiction. Target the inputs that enable mass attrition rather than solely attriting frontline platforms. Deny the adversary the capacity to regenerate strike systems, increase operational friction, and use demonstrable reach as strategic messaging that shifts behavior across civilian and military spheres. The sinking of Port Olia 4 did precisely that. It removed material, injected cost and risk into an entire logistics chain, and broadcast a capability threshold that reframed what constituted a contested maritime domain. In the weeks and months that followed, operational lessons were rapidly institutionalized. Defenders prioritized multi-sensor fusion, littoral radar densification, and mobile counter-UAV packages. Attackers and observers codified the utility of long-range unmanned strike packages paired with layered surveillance to exploit predictability. Commercial networks adjusted contractual terms and route planning to mitigate exposure. Above all, the event collapsed an important psychological barrier. Modern precision, intelligence-driven strikes can reach beyond traditional perimeters, and the concept of a rear area sanctuary is conditional. In the contested maritime environment that emerged, protection, dispersion, and rapid replacement became the currency of resilience.